Alright gang, we've made it. We have done our slog through those other boring senses and we have arrived at the coolest sense of all, audition. We're going to spend more time on audition than we've spent on any other sense, and we'll spend even more on vision. And that's not just because I like audition the best, it's because it's one of the most important senses for humans and because we know the most about it. I hope to convince you over the next couple of weeks that our ability to process sound is really pretty impressive. To demonstrate just how incredible the auditory system is, I want you to imagine this. Imagine a lake, like maybe Lyman Lakes. There are two narrow channels dug up into the side of the lake, and across each channel is stretched a single handkerchief. Now, using only information about the motion of the handkerchiefs, I want you to answer the following questions. How many boats are on the lake, and how far away are they? Just totally impossible, right? All the boats are making waves, and there's like ducks and fish and whatever that are also making waves, and all those waves are mixed together. So the motion of the handkerchiefs is going to reflect a ton of waves from lots of different sources. How could you possibly know what's coming from each source? But this is exactly what the auditory system is doing all the time. The two narrow channels are our ears, the handkerchiefs are our tympanic membranes, and using only information about how our eardrums are moving, we're able to identify where things are in space, how far away they are, how many people are talking in a crowded room, whether it's a big dog barking or a small dog barking. We have access to a ton of information about the auditory scene, but we're doing it using only the analog of handkerchiefs moving in the waves of the water. All right, so today we're going to be focused on the stuff of sound. That is what the signal is and how do we measure and describe it. Then we'll go on to talking about what the auditory system does with sound and how transduction works. So sound, as you read, is pressure propagating through some kind of medium. We visually represent those compressions and rarefactions of matter using these kinds of waveforms that signal the frequency of a wave and the intensity of it. Now, the key is that the medium that sound moves through has to be compressible. It needs to have something to move through in order to propagate. So this is typically air, but of course sound can move underwater, or if you've ever listened through a door and heard voices moving through the solid of the door, you can tell that sounds can move through solids as well. So there has to be something for the sound to move through. So, in the 1979 movie masterpiece by Ridley Scott, Alien, it's true that in space, no one can hear you scream because space is a vacuum, and so there's nothing for the sound to move through. Now, it's important to point out that humans can't hear all of the frequencies that are possible. We have a range of hearing of about 20 hertz to 20,000 hertz. So to give you a sense of what a really low-pitched sound would sound like, here's one that's about 100 hertz. And here's one that's about 12,000 hertz. The reason that I didn't do all the way down to 20 hertz and all the way up to 20,000 hertz is that most kinds of speakers, especially like your laptop speakers that you're listening to this out of, probably can't produce those frequencies. So some other animals can hear frequencies that humans can't. You can see dogs and dolphins can hear sounds that are much higher than 20,000 hertz. Some animals, like elephants, can hear sounds below 20 hertz. We call that infrasound. So humans are sensitive to this range of 20 hertz to 20,000 hertz, but we're differently sensitive to it at different frequencies. So what this curve is demonstrating is that we are more sensitive to sounds at about 2,000 hertz than we are to sounds more like 20,000 hertz or more like 20 hertz. Now, although humans can't hear infrasound, we can't perceive it, it doesn't mean that it can't affect us. So it may be perceptible without being audible. Infrasound can be caused by natural things like lightning or earthquakes. Some animals, like elephants and whales, can produce it. And it can also come from human-made sources like wind turbines, some kinds of specialized speakers, and some engines and fans. Now, infrasound can have really interesting physiological consequences on humans. It can lead to unpleasant reactions like sleep disturbances, headaches, difficulty concentrating, dizziness, ringing in the ears, or a sensation of oral pain or pressure. In fact, infrasound can cause the fluid inside the eye to vibrate, which can lead to hallucinations. So some scientists have suggested that when people feel shivering down their backs and unexpected nervousness and think they see ghosts, In fact, they may just be in the presence of infrasound. All right, so we have two ways of characterizing sound: frequency and amplitude. All of the sounds that we're going to talk about, we can characterize by just describing them in terms of frequency and amplitude combined in several different ways. So the kinds of sounds that we've talked about so far are what we call pure tones, a single frequency playing at once. But many of the sounds that we are interested in describing, like voices and instruments, are much more complex. So the reading started to go into this, but today we're going to unpack this in more detail because it's going to form the basis of a lot of what we do in class. So today I'm going to talk through 4 critical points about complex sounds, like instruments and voices. And then we'll use those 4 points to understand one of the coolest auditory illusions ever. Okay, so most sounds that are perceptually interesting to us, voices, instruments, etc., are combinations of lots of frequencies being played simultaneously. So for instance, this complex note that you see at the top is a combination of lots of different pure tones. Now, this may seem surprising because if I make a note with my voice, if I say, ooh, it just sounds like one note, right? It sounds like it's just one frequency, like one thing is happening. But in fact, it's impossible to make a pure tone with your voice. It's also impossible to make a pure tone by pressing a piano key or plucking a guitar string. So any complex note, like this, is made of a combination of lots of pure tones. So what are the multiple frequencies that are present? Well, we most commonly describe sounds based on their fundamental frequency, that is the lowest frequency that's present. So what we would call an A440, that is the A above middle C on a piano, we call A440 because the lowest frequency present, the fundamental frequency, is 440 hertz. So there's a 440 hertz sound present, but there are other frequencies present as well. So what are those other frequencies? Key point number 2. Hit it, key, like a musical key. Okay. The other frequencies that are present in a complex note are called the harmonics, and those occur in multiples of the fundamental frequency. So here's a Fourier spectrum, like you read about, showing the frequencies that are present for a violin playing a note that has a fundamental frequency of 392 hertz, shown on the left in red. Each of the other harmonics that are present are spaced precisely 392 hertz apart. So first it's 392, then 784, then 1176, and so forth. So harmonics always occur at these nice tidy intervals for instruments and voices and most other naturally produced sound. There are several different ways that we can visualize these sounds. The reading introduced you to this kind of Fourier spectrum, which shows which frequencies are present from a single source, where frequency is shown on the x-axis and the height of the lines represent amplitude. However, it's also going to be useful for us to be able to visualize complex sounds that come from multiple sources simultaneously. So in order to visualize that, we need another tool, which is the sound spectrogram. Spectrograms show all frequencies that are present at a particular time and unfold over time from any number of sources. So here the x-axis is time and the y-axis is frequency. The different colors you're going to see represent amplitude. Blue is quiet, pink is louder, red is even louder, white is the loudest. So this shows a piano playing middle C, which has a fundamental frequency of about 261 hertz. So the even spacings that you notice indicate that there are big bursts of amplitude at these regularly spaced intervals where the harmonics are. And you can see, again, that these are occurring at regularly spaced intervals that are all 261 hertz apart. I included the link on Moodle so you could mess around with the spectrogram in real time and see for yourself that multiple frequencies are present when both voices and instruments make sounds and that the frequencies are evenly spaced. So in case you didn't get a chance to mess around with that yourself, here's a demonstration of what it looked like when I was talking strangely to the computer.
Hi there. Ooh. Bye-bye.
So our key points so far are complex notes are made up of multiple different frequencies, and those frequencies occur in regular spacings that are related to the fundamental frequency. But why do the harmonics occur in multiples of the fundamental frequency? The answer is physics. Here's how it works. When a string or vocal cords or anything else that makes complex notes vibrates, the strings don't just swing back and forth fixed at the ends. If that were the case, they would always produce pure tones. Instead, when a wave reaches a fixed point, like the end of a string, the wave travels back in the opposite direction, resulting in a second harmonic. The motion of these waves canceling each other out and amplifying each other as they move down the string and back up the string render these complex patterns. So watch these strings in action, and you can see for yourself that these aren't just like sine waves moving back and forth along the string. They're actually producing complex waves that look like the waveforms that they result in. So another question is that if we have lots and lots of frequencies that are present at the same time, what frequency does a complex sound sound like? That is, what pitch do we perceive a complex sound to be? The lowest one, the highest one, some combination? When we hear a complex sound, we report that it sounds most like the fundamental frequency. If I were to ask you to hum all of these pure tones, what you'll try to do is match the fundamental frequency of your voice to the pure tone that is the fundamental frequency. So when I play this complex tone, if you try to hum that, and then you also try to hum this one, you end up humming the same tone. So even though all of those pure tones are present in the complex tone, what we perceive the most strongly, the height that we perceive that complex tone, that complex note to be, matches the pitch of the pure tone. So one thing that we could say is that the perceived pitch of a complex tone is the lowest frequency present, the fundamental frequency. So let's play with that a little bit. Okay, so this is an idealized spectrogram where the bands are representing the harmonics of a digitally produced sound. The fundamental frequency here, just looking at the one on the left, is about 250 hertz. So we've got harmonics at 500 and 750 and 1000 and so forth. And here's what this complex sound sounds like. Now the next one, this next column here, is a digital version where we have cut out 250 but maintained the rest of the harmonics. So this is only possible with digital audio editing, to selectively remove only the fundamental frequency and leave the others. We can only do that digitally. So if the perceived pitch depends on the lowest frequency present, this column should sound much higher pitched than this one, right? We've had a big jump in the lowest pitch present. So let's listen to the first one again. And now listen to this one. It sounds the same, right? I mean, maybe the quality sounds a little different, it sounds a little tinnier, but it does not sound like it has suddenly gotten much higher pitch. If you try to hum it, you're still like humming the same pitch. We're still perceiving that as being the same pitch height. Let's do it again. Let's take out another frequency. So now we've pulled out the 500 hertz tone as well. And how does it sound? Still the same. So what's going on here? It's clear that we do not just hear the lowest note present and perceive that as being the pitch of the complex tone. We call this the illusion of the missing fundamental frequency, and it demonstrates that the perceived pitch of a complex note doesn't change even if the fundamental frequency is digitally removed. So that means that the fundamental frequency can't be all that is governing our perception of pitch height. So here's what's going on. It has to do with point number 3. I said before that perceived pitch depends on the fundamental frequency, but that is because the fundamental frequency governs the spacing of all of the other harmonics, not just because it is the lowest tone that's present. So in a tone with a fundamental frequency of 220 hertz, the harmonics are all neatly spaced 220 hertz apart. In a sound with a fundamental frequency of 440 hertz, the harmonics are all 440 hertz apart. So what we are hearing when we hear the fundamental is not necessarily the lowest note that is present, but what spacing the different harmonics have. So we're hearing those regular spacings in between the harmonics. So that means that if I were to take away the lowest frequencies, if I digitally remove that 220 for the 220 hertz tone and the 440 for the 440 hertz tone, if I just pull those out, you can still tell what the pitch is. The height of the pitch remains the same because the fundamental frequency is encoded in the spacing of the other harmonics. This is bananas. right? How do we know how high-pitched something sounds? We listen to the silences between the frequencies that are present. We have to figure out what kind of fundamental frequency could have generated that sound. And so we hear the fundamental frequency even when it isn't actually there. So this isn't just a fun trick. We infer the fundamental frequency from missing information all the time. For example, when you make a phone call, the data that your cell phone transmits does not cover the full range of 20 hertz to 20,000 hertz that humans can hear. Typical cell phones convey information from about 300 hertz to 3,500 hertz, shown here in the dotted black lines. But a male voice can have a fundamental frequency near 100 hertz, well below the 300 hertz limit of what the phone can transmit. So when you hear a male voice on the phone, it sounds lower pitched than your phone is capable of transmitting. You hear a fundamental frequency of 100 hertz, even though the lowest sound your phone can play is about 300 hertz. You are literally hearing things that aren't there. So you're filling in the inferred pitch height based on the spacing of the other harmonics. You may be able to tell that voices sound a bit different on the phone than they usually do, and that's because you're not getting that information about the very high pitches that voices can convey that you would listening to someone in person. At this point, people often ask if this is also why your own voice sounds different in recordings than in real life, and that is from a different mechanism that we'll talk about next time once we've covered auditory transduction. Okay, so what we've got so far is complex sounds are made up of lots of different frequencies. What are those frequencies? They are multiples of the fundamental frequency. And how does it sound? The height of the sounds that we perceive, the pitch that we are perceiving, sounds like the fundamental frequency, but the fundamental frequency doesn't actually have to be present in order for that to be true, because we can infer the fundamental frequency from the spacing of the harmonics that are present. Okay, so here's what's missing. If a flute and a violin are both capable of playing a note that has the same fundamental frequency, that means they'll produce the same harmonics, because harmonics are always multiples of the fundamental frequency. So why do a flute and a violin sound different? Here's point 4. The timbre, or quality of a note, is determined by the relative amplitude of the harmonics. So a flute and a violin playing a note with the same fundamental frequency will produce the same harmonics, but the relative amplitudes of those harmonics will differ. So for a flute, the second harmonic is a lower amplitude than the third, meaning the second harmonic sounds quieter than the third harmonic. Whereas for a violin, the second harmonic is a higher amplitude than the third. Here's another difference. At the very high harmonics, the amplitudes drop off a lot for the flute, but they're still pretty high for the violin. So different instruments each have the distinctive sounds that they do because the amplitude of the harmonics they produce differ. So I said before that we could describe sounds using just amplitude and frequency. Now, timbre is also a way that things sound different from one another, but we can break timbre down into the amplitude of the different frequencies that are present. All right, I'm going to play you the Shepard scale. It's a series of notes. I want you to just listen closely and notice how the notes are changing over time. All right, here's the first note that I played you, the first note of that scale. And here's the last one. It's going to be way higher pitched, right? Because each of the notes got successively higher pitched. What? I can hear you gasping all the way from here. This is an auditory analog to like an MC Escher staircase. It seems like the notes are getting higher and higher pitched, but it never actually goes anywhere. How can this be? It's in key points 1 through 4. Here's how it works. So a Shepard scale is composed of notes called Shepard tones. Here's an example of one Shepard tone that's made up of primarily 3 different frequencies. They have energy only at harmonics that are doubles of the previous harmonic. So if this were a regular note with a fundamental frequency of 220 hertz, it would have harmonics at 220, 440, 660, and 880. But here, the 660 is missing. The spacing of these harmonics means that there is not a consistent gap between each of the harmonics. Every harmonic is a different distance from every other harmonic, so the fundamental frequency is not clearly specified. So maybe it's a 110 hertz note, but the 110 and the 330 and the 550 are missing. Maybe it's a 220 hertz note, but the 660 is missing. When all the harmonics are different distances apart, the height ends up being somewhat ambiguous. We can't actually determine what the height is. So now we add in a second note. Again, all of the spacings are unequal, so the height is somewhat ambiguous, but each of these harmonics are slightly higher pitched than the ones in the first note. So when the height is ambiguous, as it is for both of these, and most of the energy is somewhat higher pitched in the second note than the first, we perceive that as the height increasing. We could be fooled into thinking that these notes are higher pitched or lower pitched than they are, but when we have a clear contextual cue that all of the energy is slightly higher in the second one than the first one, that indicates to us that the tone is getting higher pitched. So you can hear how these sound. So it clearly sounds like they're getting higher. All right, let's add in another one. When we introduce a third note, the pattern continues, but the highest frequency that's present, that 900 hertz tone, is now getting very quiet. And some of the very quiet low frequency notes are being introduced as well in that third tone. We don't immediately hear those low frequency notes coming in because they're so quiet relative to those loud mid-frequency ones. So this pattern continues. The loudest notes are in the middle frequencies, and those are getting higher pitched at each successive step. The really high pitched and the really low pitched ones are also moving, but they're quiet enough that they aren't as perceptually salient. So as we add in more and more, you can see that over time, the frequency band that started off at 220 hertz and gradually gets higher and higher pitched until it is representing about 440 hertz and is actually the exact same signal that was the first note that you heard. So we end up with a note that starts here and ends up here. Each step sounds higher pitched, but we haven't actually moved at all. How cool is that? All right, next I'm going to show you how Shepard scales can be used cinematically.
The ticking makes way for an overwhelming orchestra that seems like it's rising higher and higher, but never actually does. It's so tense, it makes you cling to your seat. That is because Zimmer is taking advantage of an auditory illusion caused by something called a Shepard tone. It consists of several tones separated by an octave layered on top of each other. As the tones move up the scale, the highest pitched tone gets quieter, the middle pitch remains loud, and the lowest bass pitch starts to become audible. Because you can always hear at least two tones rising in pitch at the same time, your brain is tricked into perceiving a constant ascending tone. Loop it all together, and it sounds like a piano scale going on for infinity. When the transition between tones is continuous, it's called a SHEPARD-RISSET GLISSANDO, and it can sound really spooky. This can happen in the opposite direction too. You can hear it in the endless stairs in Super Mario 64, and in Pink Floyd. It's like a barber's pole of sound, constantly seeming to rise without actually going anywhere. Put that in a soundtrack, and it creates the sound of rising tension that carries the screenplay forward.
This is where I'll leave you for now. If anything was fuzzy, I'd encourage you to go back and rewatch, because in the problem sets in class and then in the next lecture, we're really going to be building on these concepts. And as always, if you have questions, I'm happy to hear from you. Okay, so as we go from A to B, the frequency changes, which we perceive as a change in pitch and measure in hertz. As we go from A to B here, the amplitude changes, which we perceive as a change in volume and measure in decibels. That lovely sound sequence was C. So it sounds like it's going from medium pitch to low pitch to high pitch. Although there's also an amplitude change in that first section to the second section, the thing that's the most perceptually salient that you will hear the most clearly is that change in pitch. Number 4, these are going to differ in complexity. So because the note contains harmonics, the timbre or quality of the sound will differ from a pure tone. All right, so this is a throwback to the example in the video. Even if you can't see or hear the fundamental frequency, it is still apparent what it would have been from the regular spacing of the harmonics. All right, well, let's listen. Here we're gonna go from A to B to A to B. So B sounds lower pitched than A, which is weird because all of the frequencies that are present in B are higher pitched than the A frequency. It's because the regular spacings of the harmonics in B implies a fundamental frequency that's missing. So A sounds higher than B, even though all the frequencies in B are higher, because the implied fundamental frequency of B is lower. You're hearing things. This is a tricky one, right? These make up an illusion that's called the tritone paradox. So you may recognize that these are shepherd tones, meaning that the spacing of the harmonics is inconsistent, so it doesn't clearly specify a fundamental frequency. As we go from the first panel to the second panel, some of the frequencies get higher and some of the frequencies get lower. As we move from the first panel to the second panel, there are some frequencies present that are higher pitched and some frequencies present that are lower pitched. So it's truly ambiguous whether this is going to sound like it's getting lower and then higher, or if it's sounding like it's high and then getting low. So let's see what it sounds like. So in each of these 4 examples, I'm going to play 2 tones, and I want you to determine whether it sounds like it's getting higher pitched, like it's going doo doo, or it sounds like it's getting lower pitched, like it's going doo doo. So listen closely and make a note. Actually, please write down for each of the 4, 1, 2, 3, 4, if you think it's getting higher or lower pitched. Then we'll compare answers when we're back in the big Zoom room. All right. If you are doing this on the regular schedule, meaning it is class time, please stop watching now. Turn it off. If you are doing this on your own schedule, I'll explain a little bit more about it in the next slide. There's tremendous variability in what people perceive here. So in each of these 4 examples, you hear 2 notes, and some people will say that as you go from the first note to the second note, it sounds like the second note gets higher. Some people will say it sounds like it gets lower. If you look at the numbers here, you can see that there's a really even split on some of these. For example, in the second and third ones, when I play those, half the people will say it sounds like it's getting higher pitched, half the people will say it sounds like it's getting lower pitched. So why the variability? Why can I present 2 people the exact same stimuli and have them hear them quite differently? It isn't well understood. There's some speculation that the way that we perceive the tritone paradox has to do with where we were raised and the linguistic patterns that we hear the most often, but I don't find that evidence terribly compelling. Hopefully we will hear more about this awesome illusion so we can better understand it in the future. Take care.